and you'll find mistakes. Poor guy.
But in spelling of his name.
Okay, it was already noted that most people needed to find their own way to understand cluster expansions. Often they were using it as a tool in some other consideration. For example, expansions are indispensable if you want to estimate surface terms of partition functions, but they were using the expansions without actually understanding them. This was my case, for example. So I will present you my attempt to find and understand what these expansions and cluster expansions and Meyer expansions are, to try to persuade you that the combinatorial approach is really the most simple and most powerful from among the other approaches. I will present some alternative methods. I don't know whether they are really new or not. Maybe they are well known to specialists. Anyway, I will show you a different method of summation than usual. I will show you kind of Kotetzky price, but not estimate, but equation. And if time permits, I will show some special methods for hard repulsive case suitable for models like determinants or Gonzaga description of unique model giving results which are close to exact, which give way to close to exact solutions. Okay, so we will study Meyer expansions of polymer models. Polymer models. Oh, maybe I would prefer the big one. Yes. Here is a guess of interacting polymers. This is the interaction constant, the compatibility constant between polymers. This is the repulsion, soft repulsion case. If F equals to -1 or 0, it is hard repulsion case. And as Alan explained, usual polymer models can be written in such a general form: sum over ordered entuples of polymers, product of weights of polymers, and here is the product of compatibility coefficients, which is expanded, gives sum over graphs on the set of indices. And these terms are product of compatibility coefficients of pairs of polymers. In fact, sometimes I would be tempted to write here minus, because very natural models of polymer models have already their minus here, like determinants of matrices of Laplacian type, or if you take Kramer-Svanier description of Ising model and introduce the proper complex ways, then you also have minus. But of course, in most natural situations, physical natural situations, here this is the Gibbs factor E2 minus energy of the contour. So the result of expansion is that the polymer partition function is written as exponential of the sum of clusters. Clusters are collections of polymers which are connected in a way that this term is non-zero. F is sum over all connected graphs. And okay, so this is Meyer expansion. It was already explained here. Our next step will be to estimate, to give some relations for conversions of this cluster expansion sum. This one. You can measure these conversions by looking at quantities which are traditionally denoted by A. A is the sum of cluster expansion terms over clusters touching a given polymer. This touching can be expressed, I will explain it later, in soft case, such a coefficient, and then there will be, so what I'm doing is outline what I will say in more detail later. And then there is a relation, there is an equation, not inequality that A is bigger than something, but equation that A is equal to sum over clusters, over polymers touching given polymer, gamma, otherwise this is 0. And here is some integral because I will have to introduce some artificial parameter as is usual. And here is E, so this relation explains why there is exponential to E on one side and E on the other side. And there is this integral because there should be a taking a derivative with respect to this auxiliary term. I will say a few words about resummation, which is different. I don't know whether better or worse than usual resummation by Penrose trees. Instead, I will use some hierarchical structure, which I call left tree. Maybe they have some other name, which are very simple. I'm not saying that they are better, but they are suitable for some purposes also. And finally, I will say a few words about a hard repulsion case. In hard repulsion case, if you look at these cluster expansion terms, then you see many cancellations. And what remains are objects, which I call cactuses, which look like this. There is
special class of trees.
special left trees. Some factorized graphs. I will explain. Tau, this is C. C is a letter for cluster, and tau is letter for left tree.
It's the same function of fg.
Well, this is function of different variables, so there should be some relation between this quantity. I will give.
It's not the same function.
It's not the same.
Not the same, but because it's quantity for different variable. So I should use a different letter,
So with three
perhaps.
you have f with three different types of subscripts denoting three different functions.
Yes, precisely. Okay.
Maybe you have different fonts.
Some notation. So this is the usual polymer partition function in the hard repulsion case, which is written, as I already noted, in such a way. Expanded, the terms of expressing incompatibility are expressed. You get something like this, and then this is just for notation. So cluster is an ordered n-tuple of polymers. Weight of a cluster is 1 over factorial product of polymer weights. F of G is the product of incompatibility coefficients of the pairs of the polymers appearing in the graph. Okay. And this is my expansion, which I already noted. Take example as a test. 1 plus x equals to this. Sum over connected graphs.
I mean, what is this using?
Oh, well, this is just comment how to prove this theorem.
Oh, I don't understand the formula.
This is very trivial. This is and attempt to understand why you have this formula. E to the sum is sum over n tuples of variables which are taken from the set of these variables. Just an attempt to explain. You can forget it, you know, this is just a remark for those who do not know the Meyer expansions. Those who know it forget this trivial formula. So this is Meyer expansion, and then I will go to Kotetzky price equation. So these are the cluster expansion terms. These are terms which should be -1 or 0. 0 if this cluster does not touch gamma, and -1 if it touches gamma. So the useful way how to write it in general cases follows. You know, if f is equals 0 or -1, this equals to either to 0 or to -1. And then I use a trick which is very standard, using artificial new variable t from 0 to 1, and I consider new model. Why I'm doing it? Because how you want obtain the Kotetzky price equation? You take sum over clusters touching a given polymer, and then you want to say this polymer is responsible for touching, and the rest forms an exponential. But the problem is that there could be several polymers touching a given polymer, and this gives you this makes you problem in obtaining equation. It's not problem for inequality, but it's a problem for equation. If you want an equation, then a very simple way is to introduce a parameter here, t, and take a derivative of the product, and derivative of the product contains terms. At each parenthesis t disappears, and this gives you proper term on the right hand side. So I will show the result.
You simultaneously soften all of the f's.
Yes. So once again, what I am doing is that I soften the repulsion. I have a polymer gamma, and I soften the repulsion with all the rest, with all the polymers touching gamma, by factor t. That is, instead of f, I take tf. For t equal to 0, that is that I make gamma independent of the rest, and for t equal to 1, this is the original model.
But you're only doing it for the ones that are actually touching, not for all of them simultaneously.
I am doing it for one particular gamma. The rest of the model is left untouched.
You mean the guys who are touching gamma
Yeah,
don't have their interactions with each other change?
Not change with each other, change only with gamma. The rest of relations between other polymers is left untouched, and only the interactions with gamma are changed.
But if some of the guys touching gamma happen to be gamma
of course, yes, gamma with gamma is also softened. Very similar notion is, so T relaxed in this parenthesis and T relaxed in this parenthesis, something very similar. That I have a new model, forget for gamma, remove it from the model, and then you have a new model where weights of all polymers are multiplied by this constant, 1 plus T.
Oh, I'm sorry, you have two different models. One of them is parentheses T gamma relaxed?
Well, these
Yeah,
models
they're
are very,
brackets,
very
there
much
you go.
related. The first model is that I relax the relation with gamma, and the other model is that imagine that I fix gamma and look at the rest. And the rest behaves like a polymer model where weights of all contours outside of gamma are changed by this factor. You can look at it as a conditioned model. The first model conditioned by requiring the gamma is sitting there, presented, and everything what you start. Okay, then take the derivative of this A, and you get very simple formula, because if you take derivative of this product, then this is a sum of terms corresponding to various I, and if you take derivative of the one particular parenthesis, then this term appears. This is gamma I, and then there is, of course, summation of the rest of the cluster. You fix one piece of the cluster and sum of the rest of the cluster, and if you look at the structure, then it's precisely the exponential of this new model, change model. You know, of course, it's more complicated than before, but this is not so bad because first the model which is relaxed have weights which are small, and also the factors like the product of 1 plus t f j minus 1, which is negative. Absolute value of this is smaller than product of 1 plus f j minus 1. So the model is better in a way that weights are smaller and interaction is softer. So you can assume that bounds which you have for original model will be valid also for this relaxed model. So then you can look at usual Kotetzky price criterion. That is that there exists a quantity B satisfying such an equality, and you can ask what happens if you try to solve this equation by iteration, starting with this and looking whether it converges. And the answer is yes. If you have such a condition, then the iteration converges. So you are able to find the solution of this complicated equation. I'm not saying that it is very useful, you know, it's just a remark that there is equation. I don't have really real applications, just a remark that this is an equation giving additional light on the problem of
So are you saying this is optimization of those B's? Somehow you are, when you have equation, you have somehow optimal solution of...
Oh, well, if you have a bound, then you find solution which is better. I'm not saying how much better, you know, but it's not worse.
The solution doesn't satisfy this as an identity.
Yeah.
This solution satisfies this.
So
you
condition as an identity.
You can take this as a definition of a new A on the left-hand side, a new A, and old A is on the right-hand side.
No, what they're asking is, imagine you could solve this differential equation and get the whole function as a function of t. Would that allow you to say what's the optimal choice of B in the Kotetzky price condition, so that you could actually get equality in the Kotetzky price?
One should look at one should consider some supremum over all t's, because you are doing this softening with respect to all the polymers. Actually, if you iterate this equation,
You put t equals 1. Go back to your
t equals to 1 is the original situation.
But there is derivative, so it is not exactly...
Well, there is integral from 1 to 1, 0 to 1, so it doesn't, the bounds would be okay.
If you just look at the Kotetzky price condition, the way you get equality is by summing all the rooted trees. Because the Kotetzky price condition with equality is the functional equation for the generating function of rooted trees.
Mm-hmm.
Then the question is, what relation does that bear to the full sum?
Precisely, this is the attempt to realize this idea here.
For the connected graph.
Okay, I give it as just a remark. Maybe if people are interested, we can discuss it later. I have nothing more to say to it, you know. So I would like to say also about some methods of resummation. One resummation for soft repulsion case will be based on a notion of a left tree. I have ordered set.
What do you mean soft repulsion in this case?
Oh, by soft repulsion, I mean that the compatibility coefficient between polymers is between -1 and 0.
So polymer not necessarily interact to an alcohol. It's a positive interaction, but not necessarily alcohol.
Yes, because the interaction is 1 plus F. So
It's level 2.
It's level 2.
Or is it
Level
level
two.
1? Is it the hard, I'm sorry, the self-interaction can also be soft, right?
yes.
So it's level 1.
Yes, and in this case, what is your claim in this case?
He hasn't gotten there yet.
Now I will show you something. The resummation, it will be very simple. You know, I am not saying that it is new. It's very natural method of resummation. So I define the structure on an ordered set, which I will call left tree. Left tree is defined recursively. Left tree on such a set is defined by decomposing this set into disjoint subset of left trees, such that the left point is a singleton. This is the chief of the left tree. You know, very simple, because you have ordered set. This is the chief, and there are some subtrees. And again, the subtrees have their subchiefs and so on.
I'm sorry, do the subtrees have to be intervals?
Ordered set, no, not interval, of course, no, not, you know.
So isn't this just a rooted tree where the children...
It's some kind of,
Is it just a rooted tree where you also specify a linear order of...
something like this. Should it have some proper name in combinatorics? I'm apologizing that I do not know the proper name.
Rooted plane tree?
Plain
So
plant
the
tree.
root is given, and then the children of each parent have an order.
So we have a decomposition of an ordered set. Each set of the decomposition has its natural order, and here is the chief and so on.
So you're not saying that when you go from parent to children, the labels are increasing?
Yes,
Take the
yes,
minimum. Each time you take the root has to be the minimum of the.
yes.
So it's increasing. Planar.
I see, that's what you call it?
Right? So it's yeah.
You know, there is an interesting remark. If you denote by L the number of left trees on a set with a cardinality M, then it satisfies such a recursive equation sum over all the composition such that the first point is a singleton product of number of of left trees in the subset. And what is funny, it is the same equation as for the number of cyclic perturbation. This is trivial but tricky, you know. If you look at the number of perturbations, cyclic perturbations, here is 1, and the rest is the perturbation, and perturbation is decomposed into cycles. So in such a way, you see that the number of cyclic perturbation satisfies the same relation. Number of cyclic perturbations now is m minus 1 factorial. So number of left trees is m minus 1 factorial.
This is one
Question: when you see collection of disjoint subtrees, do you assume an order on the?
I have substructures on subsets, which are again decomposed by taking the left point, which.
But these substructures, they are ordered, or
Yes, because you have order which is somehow hereditary for subsets.
So that's the classical bijection between permutation and planar tree, increasing planar tree. I understand that. And it's contained by n factorial.
And now there's a small remark, expanding of logarithm, and
Yeah, it is. We lost the
Down.
line.
this is a trivial remark. I already noted the number of left trees. And now the resummation is very, very natural, you know, because you sum over all graphs, connected graphs. Connected graphs look like that. There are components if you removed all the bonds with the chief. So here are subgraphs, connected components, and then there is a number of connections from the chief to a component. You need at least one connection is required. So you take this product of connections from the chief to the subtree minus empty connection, and this term is between 0 and 1. It's negative. So you can imagine that chief is related with substructure by some minus coefficients between 0 and 1, and the same for the other components, and so on. So you continue. So you replace the graph by a left tree. Of course, if hard repulsion case, this is precisely minus. So in hard repulsion, this coefficient is precisely minus. So you pay 1 minus for each connection with the chip, with the substructure. And then you have a very elementary relation that the sum over graphs is the sum over left trees with quantities f defined in such a way, which are -1 in the hard repulsion case, and which are between 0 and 1, 0 and -1 in soft case.
So what is this F subscript T?
F yes, F of chief and
Push now, you have to push it up.
yes, yes.
No,
there we go.
there we go.
This and this is the same in different notation. Here is the subtree, the chief of the subtree. So here is the chief U, here is the subtree, and f of chief and the subtree is given by this. It's the same as written here.
So little u is the parent of all the people in big U?
Big U is a subordinate of the chief U.
And whether it is in parentheses or as an index is the same.
And you take the sum over all non-empty connections of the chief with your subordinate unit, and this is expressed as a product of this, because you can decide whether you choose or not choose this bond. Take a product over all bonds minus empty, which is forbidden. So this is precisely the sum over all possible connections of the of graphs connecting the chief with the sub.
You're somehow decomposing the Mayer weight of an arbitrary connected graph by breadth first search, starting at the root. I think you consider
Yes.
all the edges coming out of the root, and those go into certain.
That's DFS activity.
But you divide into these components. So you have
right
a,
into
you
those
have a
components
graph.
of what's connected underneath you.
You cut off everything going from the root, and then you have the subgraphs.
Right, and then you keep doing that recursion.
Okay, so that's all concerning this. Okay, so I have nothing more to say to this part. What is my point? All these are things I did not publish them because I don't know whether they are really new. And what I am really interested in are some perturbation Gaussian fields, which is difficult to use. So this is kind of preparation for this. So in the rest of my time, I will explain another method of resummation, which is very nice, but which is very special. It can be used for models appearing in the study of perturbation equations, but it is something which leads directly to exact solution of some situations. So I will explain it here because it uses, I did not know this language before, substitution of species. Substitution of species and then transformation of the object. So what I will do, I will present a method for hard totally different from this. Forget left trees. Now I will describe the totally different method of resummation, which will be for hard repulsion case and for a special situation where compatibility of polymers is defined in terms of intersection. So polymers are compatible if and only if they do not intersect. Yes?
But this is a special case of level 3 where what I call vertices and what other people call polymers are actually subsets of a set.
Yes, subsets typically having some structure, because the most nice example, of course, is if you have a cycles, something like cycles, and they intersect or not according to their supports. So I will construct something which I will call quilted clusters. Here is a picture. I substitute each bond of the graph, of incompatibility graph, each bond which has its minus, by a bipartite graph. Here is one contour, polymer, sorry, other polymer. Here is the intersection. Intersection here contains 4 points, which are common to both polymers. And I construct bipartite graph, non-empty ones, using inequality like this. That is, instead of 1 minus between 2 copies, between the 2 polymers, I consider the whole collections of bipartite graphs of this kind.
These 4 points, they are really intersecting.
They are intersecting.
How you double them?
Well, the picture maybe is, these are the same points. Yeah.
And you introduce auxiliary
Yes.
edges there.
So your polymers are subsets of some other set, call it S.
Yes.
And you're on the set S.
Yes, I have subset lambda. In fact, I will need some order, so I will be order on this set. Soon I will use it. And I have polymers gamma, which have support, say, P, and incompatibility F gamma gamma 1 is equal to -1 if and only if P supports of contours of polymers do intersect.
But then I don't quite understand what you're doing. You're saying if the intersection is non-empty,
Yes.
let's look at what this intersection set is. For example, here it's 4 points.
And
Then what do you do?
consider collection. I will construct new objects, which I will call quilted clusters, which will be clusters, but enriched by structures that in place of any bond of the graph, you will place any.
I'm sorry, cluster is a synonym.
Cluster is a
what?
connected collection of polymers, and and a graph. This is a cluster in this case. So I'm summing over connected collections of polymers and connected graphs on them. And each such structure, which I call cluster, that is a collection of polymers and a graph, will be replaced by many structures of this kind, simply by replacing the bond of the graph by bipartite graph of this kind.
By all possible
possible
bipartite graphs other than the one with no edges at all?
Exactly. Okay, why this construction is useful? It looks that you are doing things much more complicated, but only temporarily. You know, this is the quilted cluster. You know, each bond of a graph is replaced by bipartite graph. And now comes simple but extremely important observation. Take ordering of your lattice. Take the chief point, the smallest point of your lattice, and look at the structure of your quilted clusters. More precisely, forget all the bonds appearing in bipartite graphs there between these chief points. There can be many of them. Forget them all. Then your quilted cluster decomposes into components, very complicated components. How they look like? So there are components like this. Maybe there is a point T in some polymer, and maybe there is another point T in another polymer of this component. What I'm saying that this situation this situation will cancel, because if I organize the summations with respect parentheses in the cluster expansion sum with respect to these components, then for each such components I have a free choice either to connect this or not. That is 1 minus 1. And this term will disappear. So all terms, if you look carefully, of this kind will disappear. And what will not disappear are very complicated quilted structures, but containing the chief point T only once. The rest will cancel. So you have summation over situations like this. And now comes a final very simple trick that you have connected, you know, these are bonds from these quilted clusters. This is part of this bipartite graph connecting these two pieces, and so on. So you obtain connected set, and now you know that sum of -1 to the, so remarked here many times, I think also Roberto remarked it, that -1 to number of bonds in a connected graph on 1 to the m interval equals to -1 to m-1, m-1 factorial. n-1 factorial is the number of cyclic ordering. So here comes the final consideration. So what remains is the summation of an object like this, that they obtain only one copy of a chief point because the rest is cancelled. Of course, many components like that, and they are connected by connected graphs. But the sum over connected graphs is the sum over cyclic perturbation. So you can replace this sum by structure like this. You have cycle in a plane, and there are substructures, quilted clusters, but containing only one copy of the chief point of this kind. Then you can iterate this procedure. That is, you obtain object which I call cactuses. I don't see them. Maybe here in the beginning. Okay, I don't. cactus, it will look like that. You have cyclic order in a plane, and then you have object like this. Again, some cyclic order and some substructures, and each of the substructures again has similar form. Of course, you see that signs are the same for the objects. You see the well-known property of positivity of coefficients by multiplied by -1 to the -1. I have to stop.
Well,
I think
quickly,
I think it's time to stop. It's time to stop. Okay, thank you.
Well, no, I mean, go on for a few more minutes.
Oh, I don't have much to say actually. Thank you.
Any more questions?
So Milos, do you hint at some criterion out of this mobility criterion?
Criterion concerning which?
The second, let's say, this cactus.
You mean here or you mean Kotetzky price?
Either, I mean, do you
Well, I would say
forecast?
remark about this. Please, one remark I forgot to say. This looks like an exotic structure. It is not so bad because if you had the basic examples like on Zagreb is a little bit more complicated, but very similar. But take determinant. Determinant, which is of course exponential of the sum of the traces. That is the sum over all closed paths. There is a very natural way how to interpret paths, closed paths, as cactuses of cycles. In determinant you have cycles. Here you have paths, and each path can be interpreted as a cactus because how? Because if you take closed path, here is the picture of the closed path. Look for the appearance of the chief, and then you can depict the closed path in the following way: cycle, and that is different visits of the chief and subpaths, and so on. So in that way, you have unique representation of a closed path as a cactus of cycles. In such a way, the cluster expansion result which we have converts into sum of the closed paths, which is exactly the step which is taken in Zagreb solution before you take the Fourier transformation and compute the traces using computing the spectrum. So it shows that the method is natural because in such a case it gives what it should give.
Maybe I should talk to you after this, because Malik and I had something which Xavier realized a long time ago before us, which is a little bit similar to this.
There's a proof, basic proof of this with Gibson cycle.
Yeah.
Cactus are in bijection with Gibson, this is exactly.
So this Hipov cycle is this, it looks like, no?
So there is a bijective proof of the Jacobi identity on the,
Yes.
with the path and Gibson cycle.
Yes.
So if you do this proof, then you get exactly the,
Yes,
another
yes.
bijection with the cactus.
Oh, very good.
It's the same thing in different languages.
Let's thank the speaker.